Wolfgang, please.
So thank you very much. So the reason why I was here last week and this week is, some time ago and this week, is because I'm actually would like to make this interface between quantum simulation and machine learning. And actually, the talk that I would like to present here also goes exactly in the direction that we just heard in the last two questions. How do we actually make this oracle that we need for quantum machine learning? So many of the quantum algorithms that we know have this exponential speedup given an oracle. And this oracle is that we can exponentially reduce the size by using a quantum RAM or a quantum database, as Jake just introduced. And to do this, what we need, Enrique, if you say we have to download data from the internet, we would download our tools, for example, and we want then to have an oracle that actually makes this into a superposition. Now, for us physicists, we would probably translate this into bits and spins. So this means we would like to translate a list of bit strings into a quantum superposition state, and we want to make this fully programmable. Now, this is by some people considered the holy grail of quantum machine learning and many quantum algorithms. And probably, at least to my knowledge, Seth Lloyd is one of the pioneers or the pioneer of this field. And they actually introduced this word QRAM and also introduced an implementation of this. And if this is, so to say, a digital approach, and if you look at it, then what you immediately see is that it requires an exponential number of qubits and also an exponential number of gates. So the qubits would basically represent registers, which would be, so to say, these numbers here. And in order to program an arbitrary superposition, you will need an exponential number of these. Now, on the other hand, if you think about coming from a completely different side, if you think about quantum simulation, so this means we have Hamiltonians and we have a Hamiltonian dynamics, then we know actually that there is huge quantum superpositions already available. I just want to mention the systems that we think about, ions, superconducting qubits, or atoms. Then if we just look at the atoms, I mean, we can do this for all the other qubits as well, but let's only look at the atoms. There's experiments, for example, by Emanuel Blocher or Greiner or Mr. Lukin in Harvard, where they have superpositions of hundreds of atoms. So, for example, this will be crystals, so these are really several hundred atoms which form many body superpositions. So the state that you get out is a superposition of different crystal structures. So the number of qubits is large here, but on the other hand, we don't have the control over the system in such a way that we can make arbitrary superpositions. It's more or less given by the physics or given by interactions. And so the question is, can we make them controllable? And the way I see, so to say, my research is we have, for this particular problem of making this quantum oracle or this quantum superpositions, if we come from the digital computer, it's somehow clear that we need an exponential number of qubits. The reason is that we have to cut out of Hilbert space a very small fraction, which simply means we need this exponential number. On the other hand, there's quantum simulation, and as Hans yesterday had this nice slide where on the simulation it said something like reduction, so we reduce the system very much, which on the other hand means we don't have the control to actually make arbitrary superpositions. And so what I want to try is actually to bridge this gap and use, so to say, quantum simulation tools in order to solve this computational problem and make use of Hamiltonian dynamics to make these superpositions. So I add the controllability on the quantum simulation side to solve a problem from the computation problem. So in this talk, I would like to present this paper here, which I've done together with Luca Sivera. It's a QRAM based on Hamiltonian dynamics, and instead of an exponential number of qubits, We only have a quadratic number of qubits. The starting point for this is the Adiabatic Theorem, and you've probably seen this already several times in a completely different context, namely for optimization problems. So the main idea is that you have a Hamiltonian which consists of two parts, a trivial part in sigma x basis, and what is called the problem part, which usually contains the optimization problem, and what we want to find is the ground state of this Hamiltonian. Now, if we prepare the system in the ground state of the trivial Hamiltonian, that's something that we can easily do, then we adiabatically transform our Hamiltonian, so this would be the instantaneous ground state. Then we will end up in the ground state of our problem Hamiltonian if we, so to say, switch off this part and switch on this part. Now, what happens if instead of having an optimization problem where we have a single ground state, we actually have a degenerate ground state in the end? So this means our adiabatic protocol does not go into a single state, but it actually goes into a superposition. And so to say, the question is, what actually happens here? Will we get now a superposition of these states? Will we get one of these states? Will we get none of these states? This is, so to say, the starting point. So the strategy for our QRAM is that we design a classical Hamiltonian which has as its ground states the states that we want to program as degenerate ground states. So this means we have to design a classical Hamiltonian in the C basis which has the configurations that we want to store as the ground states, and then we adiabatically prepare this state. Now, this is a classical problem, so it's not very difficult. Actually, one can show that it's always possible to design such a Hamiltonian. Think about the projector. So this would be a classical projector on our data. This is a Hamiltonian that we can always make. However, it requires all-to-all n-body interactions, so we have to make some approximations, and it turns out that a very good approximation is to do Hopfield networks to actually train this data set. But it's a classical problem, and all we have to do is we have to design a classical Hamiltonian which has the configurations that we want as the ground state. Now, if we do this and we say, okay, our final Hamiltonian has now the configurations that we want as a ground state, and we adiabatically prepare this state, will we get our superposition? The answer is no, unfortunately. And the reason is that if we do this protocol, it's not simply that we go into an equal superposition of the states that are degenerate at the end. Actually, it turns out that this is highly dependent on the dynamics and on the transitions in the system. And this question was addressed by Helmut Katzgraber in a different context, where he looked at a problem called fair sampling, where he looked in optimization problems with degenerate ground states, how the sampling compares to classical sampling. So the system that he looked at was a 5-qubit system, and the degenerate ground states are these 3 configurations. So this means spin down, and filled dots means spin up. And these 3 states have the same energy. And what he found was that there is an exponential bias. So this means if you do this adiabatic protocol, you're not getting the superposition, you're actually getting only 2 out of them, and 1 is exponentially suppressed. So the question is now, if we have programmed our Hamiltonian such that it's degenerate for the configurations that we want to store, can we now make this amplitude somehow tunable? So this is the missing piece. Can we make them equal, for example? And in order to do this, we need additional degrees of freedom. And these additional degrees of freedom we introduce by a mapping that has been introduced in this paper, where we map our Hamiltonian into a classical lattice gauge model. So the strategy is that we take a Hamiltonian which is all-to-all connected and has interaction matrices, and we represent it by its parities. So this means we translate pairs of qubits into new qubits, And the translation rule is that if two qubits point in the same direction, it's spin up. And if they point in different direction, it's spin down. So this means on each connection, we have now a qubit which measures the relative coordination of two spins. And then if we do this translation, then if we have a Hamiltonian originally like this, which is an interaction between spins, then it would translate to something which looks like a local field acting on these new spins. So you can imagine if the interaction matrix here would be, for example, a minus, then it would want to point them, the logic, these new spins upwards. If the Jij is, say, a positive number, it wants to point them downwards. So this means the interaction becomes something like a local field. Now, if we do this translation and count the number of degrees of freedom, it turns out that there is a mismatch. So here we have n degrees of freedom, while here we have n times n minus 1/2 degrees of freedom, because we have here really the number of connections that are the spins now. So this means we have to introduce constraints. So we have to somehow get away with these additional degrees of freedom, which means we have to introduce k minus n constraints. And it turns out that we can make these constraints by only 4-body interactions. So we introduce k minus n 4-body interactions, and it turns out that we can align these 4-body interactions in such a way that all the interactions become fully local. So there's no non-local interactions anymore. And with this particular numbering of the qubits, so these two numbers represent the connections that the qubits represent, and the red dots are 4-body interactions. We translate, so to say, a fully connected spin model into a gauge model with only 4-body interactions. So this means we started at a Hamiltonian, which has the usual form that we've seen very often in optimization problems, which has all-to-all Jij, so all-to-all 2-body interactions, and we've translated it into a problem where the problem is encoded in local fields, and the interactions are 4-body interactions, and these 4-body interactions are completely problem-independent, real gauge variables. So this means we can program an all-to-all matrix in local fields, and we have problem-independent and local interactions. Now, if we look at the spectrum of this new mapped Hamiltonian, then we have, so to say, two different regions. There is the low-energy subspace, which contains the original problem. So this was, so to say, our all-to-all connected problem, which we can program via these local fields now. Now, separated by a large number by the constraints is the high-energy subspace. Now, this low-energy subspace is completely independent of the constraints. So these constraints, the C's, they just need to be large numbers. But if I change one of them, so I change, for example, the strength of this plaquette or of this plaquette or of this plaquette, it only changes this upper part, while this lower part is really gauge invariant. So this means we have now an additional degree of freedom which we can change. It's these constraints, which allow us to tune the quantum paths, so we can actually change this part here, but the final state is, so to say, untouched and is gauge invariant under changing these constraints. So this means our strategy is now, can we find particular choices of our constraints in such a way that we can make equal superpositions? And, so here again, so what we do is we program our final Hamiltonian. This is a classical Hamiltonian where we store the patterns that we want to store. So this would be our numbers that we need for our machine learning algorithm. Then we translate it into a lattice gauge model, and we want to find the constraints in such a way that we can tune our quantum paths. So this means we have to tune our phases that make the transitions here in such a way that we can program the population of the final state. Now, it turns out that we can actually do this, and that's actually quite a lot of mathematics. So it's an analytical theory that we derived for this. The first observation that we have here is that the transition here is called a Keyblade-Szerik mechanism. So this means if we start our adiabatic protocol for a certain time, it's truly adiabatic. And then at a time t star, the system becomes fully diabatic. So this means here it's adiabatic, and starting from here, we are actually populating other states. And the Keyblade-Szerik mechanism tells us that this population of the other states is like a sudden quench. So this means the population of the configurations that we have in our ground state do not change anymore starting from here. So this means we reduced, so to say, the dynamical problem to a static problem because we only have to look at this point here. Then there is some other analytical things to do. One has to project into the subspace, then do a so-called Schrieffer-Wolff transformation, and on top of this, a perturbation theory. But if we do all of this, then what we get out is really an effective model only for the states that are actually approaching the ground state. And this Hamiltonian is quite interesting, so I just want to show it to you. So for this example where we have 3 states that are actually going into the ground state, the Hamiltonian has this form. And on the diagonals we see, so this t is the time here, and it's scaled in such a way that it goes to 0 at the end. So this means the diagonal elements, they die off quadratically. This is exactly the same as we have in a Landau-Sehner problem. Now the off-diagonal elements, they also die off, and they die off with an exponent which is the Hamming distance between the configurations. So this means if you store bit strings which they have a certain Hamming distance, then the off-diagonal elements, so the transition between them also dies off, but they all die off at a different speed. So this means some transitions are still possible, while other transitions are already frozen out. And the speed at which they die out depends on the Hamming distance that they have, and there is a constant in front of them. So this means if we are able to tune this constant, we can actually tune the transitions that are still possible. And the way we can do this is by looking at Feynman paths between these configurations. So let's look at a concrete example. Let's say we have 2 patterns, let's say 0011 and 1111. If we translate this into our lattice gauge model, then the spins represent the relative coordinations of spins. So for example, if there's only ones, then all the spins are pointing up. And we have 4 qubits, which means we need 3 constraints to actually make the Hamiltonian. Now, if you have 1, 1, 0, 0, it means, for example, that the connection 1, 2 would be spin up, and 1, 3 would be spin down because the first one and the third one are different. And if we translate this, we get a Hamming distance of 4, which means if we want to go from this configuration to this configuration, we have to flip 4 spins. Now let's count the Feynman paths. If we do this, so this means we have to go from these 4 guys down to all of them up. So this means in the first step, we can either flip the top one, or we can flip this one, or we can flip this one, or we can flip this one. So there's 4 possibilities. And depending on which one we flip, we actually get different energy penalties. So for example, here we are only violating this constraint, here we are violating 2 constraints, here we are violating 3 constraints, and here these 2 guys. Now in the next step, we can flip another one, for example this one, which means we are repairing this constraint and violating this one, and so on and so on. So here there's then 3 possibilities, then there's 2 possibilities, and then all of them go together. So this means we can analytically write down all the Feynman paths, and we can actually see that each of these paths is unique in the energy that it takes them. So this means the action for each of them is a unique path, and it can be tuned by choosing the strength of the constraints. So remember, for the actual problem, they are gauge invariant, but for the Feynman paths, the constraints or the strengths, the relative strengths of the constraints actually allow us to tune all these paths. And because we have this now as an analytical theory, we can actually program all of our amplitudes. So here is an example where we start with a Hamiltonian. So we programmed our Hamiltonian in such a way that these three patterns are ground states. And then we use our analytical theory to calculate these constraints. So in this case, we would get out these numbers. And then if we look at the probabilities of these three configurations, we indeed see that if we do our adiabatic protocol, we end up at the equal superposition, the one that we have programmed. And here, the comparison that I'm showing here is this effective Hamiltonian. So this is the fully analytical theory, which we then compare to an exact model. So this is just numerically exactly doing the Schrödinger equation. So we see that the models actually fit together quite well. And this was just one example. We can also say that we want 20% this configuration, 30% this one, and 51% this one. We got out different numbers, and you can see that we can actually also achieve this. So this allows us not just to program any superpositions using Hamiltonian dynamics, but it also allows us to program their amplitudes, or the squares of their amplitudes. So I think this is quite an interesting direction, because making a QRAM is such an important tool that some consider it as, so to say, the starting point for many algorithms. It turns out that if you have a QRAM, then you have exponential speedup. However, if you want to make a QRAM, you need exponential number of resources, which kind of makes sense because there is no free lunch. But what we have done is we have at least reduced the number of qubits from something exponential to something quadratically. With this, this is not just something which is interesting for machine learning, but for many algorithms. It uses adiabatic quantum computing in a different context, so we are actually going beyond optimization. We are using it to prepare real superpositions, which also means that we need a fully coherent platform. So we cannot use, for example, a D-Wave device or something like this. We really need fully coherent adiabatic quantum computing. And in this sense, I think it's also for the annealing community something interesting, where we really go into preparing quantum states and not classical states. And for reference, again, this is the archive. As a last point, I would like to thank my group. So this is my group. And actually, I also want to say that I'm looking for a postdoc. So in case you know a very good postdoc, or you are a very good postdoc, please let me know. Thank you.
Thanks, Wolfgang. So, some questions before lunch? Yes?
Professor, I want to ask you a question. Why the process become diabatic at the time t star? You mean you use a adiabatic process to make the eigenstates go from this line, but you say at time t star, this process becomes diabatic. I want to ask why.
I didn't get the last.
T star, you mean at the t star, you have a slide?
The T star, yes. The Keyblade time. So it's not an adiabatic protocol. It's not an adiabatic protocol. It's using, so to say, the scheme of adiabatic quantum computing, but it's actually not adiabatic at all. If you think about the Landau-Zehner formula, for example, no? You have, so the Landau-Zehner formula tells you that you have diabatic transitions which depend on the size of the minimal gap and the velocity. Now, if you have a situation where you approach a degenerate ground state, no matter how slow you go, you will always have at some point a gap which is smaller than your velocity.
But if the x state have no superposition, then the evolution maybe not will evolve to other x states. You mean whatever slow the process is, if the energy gap is very small,
Yes.
it will go to other states.
Yes? So the spectrum really looks like this. So this means you have, so to say, here you have an adiabatic evolution. Maybe I have this picture here with the Keyblade point. So here, yeah. Yeah. So why does it not show? So here, yeah. So here you have a. So here you have an adiabatic evolution, and then at some point you will have a gap which is so to say smaller than the square of your velocity at which you change your parameter.
G, let us postpone the discussion
Yeah.
then for the lunch. Just to have a second question from Anna.
Oh, hi. Sorry, Wolfgang. Just a quick question. How easy it's to scale up your system? So you showed us a position of 3 different ground states, but if you want to scale it up to say like 1,000,
Yes.
10,000
So
ground
what
states,
we are currently working on. So the only thing that limits you is actually the way how you approximate your projector. So if you could make arbitrary projectors, then at least from the analytical insight, there is no limitation in your storage. However, if you want to really build this on a device, then you have to approximate this. So if you write this out, then it becomes, so to say, sigma c, sigma c, sigma c, 3 body, 4 body, 5 body to n body. So this you have to approximate. Now, what we are currently working on is to do this with Hopfield Networks. So you go to only 2 body and 3 body, and then you learn a Hopfield network in such a way that the states that you want to store are the ground state. Now, Hopfield networks, and in general, if you do this approximation, there is some capacity in this. And the capacity goes linearly somehow with the qubits. So this means if you have pictures of cats, which have 8 megabytes, then you can only store 8 million cats.
So the last question. I just am really curious, if you take the basic set of concepts that you developed here and you care to speculate, what other opportunities are there in this bulk boundary correspondence for things beyond the ISING case?
So you're saying here for the final state, instead of taking the ISING state, you take a quantum Hamiltonian as well?
Just in general, when I have a gauge description or a dual description,
Yes?
I haven't heard any
Yes.
opportunities.
Yes.
Such examples.
Yes.
Where else can we go?
Yes. So I can tell you what we are looking at. So one very interesting aspect is that this also helps you so this translation into this dual space or lattice gauge space also has interesting applications for this so-called counter-diabatic theory. So if you go away from thinking about minimal gaps and things like this, but really engineer counter-diabatic terms that bring you to or design final states, this is actually something that works very well because you separate completely the interactions from the problem. So the large energy is the interactions, and by having all interactions always the same and problem independent, you can make very good counter-diabatic terms. And the second big thing is shallow circuit things like QA-OA. Here you can actually use this mapping to make fully parallelizable gates and also introduce interesting additional non-stochastic terms.
Thank Wolfgang and all the speakers.